Okay, so for each of these problems, your goal is an integral, but you should not begin with an integral. Instead, we're going to demonstrate that we understand the concept of slicing, how to translate slices into an integral. So we're going to start by drawing a typical slice, then we're going to write a summation, a limit, and an integral. Okay, so I want to use vertical rectangular slices. So I should add that word in there. Vertical rectangular slices to set up a definite integral to calculate the area of the shaded region in the figure below. Okay, we do not have to evaluate this integral. We just need to set it up. So I'm going to draw a picture of my slice. This is a random location along the x-axis between 0 and 2 that I'm going to call x sub I. And the height of my rectangle will be the distance between the top function and the bottom function. So to find that distance, we would just subtract. And then the width of that rectangle is delta x. So I'm going to blow this rectangle up a little bit. Its width is delta x, and its height is the y on top minus the y on the bottom. So the y on top is the height of the linear function at x sub I. So 6 minus 3xi. Minus the height on the bottom, that's the height of the curvy function underneath the x-axis, also evaluated at the point at the x value x sub I. So this is x sub I squared minus 4. So when you simplify this, you get 10 minus 3xi minus x squared. Just distribute the negative and combine like terms. All right, so the area of that slice, that one single sliver of a rectangle, its area is base times height. My base is delta x, and the height is 10 minus 3xi minus xi squared. So then I'm going to draw a bunch of these rectangles, n of them. I'm going to draw n rectangles moving across here like this. N rectangles. So the area of all those slices is the sum, where each slice has the area 10 minus 3xi minus xi squared delta x, and I'm going to add up n of those slices. And then n of those slices is going to be a decent approximation for the area between those two curves. But if I want the exact area, I take a limit as the number of slices goes to infinity. So my area exact is the limit as the number of slices goes to infinity of the summation of n slices. And that is a limit of a Riemann sum, which is the definition of an integral. So this becomes the integral. You drop the xi's when we translate to an integral. So this becomes 10 minus 3x minus x squared, and the delta x becomes a dx. Now I have to think about my bounds of integration. I'll go back up to my picture. And I am stacking up these slices starting at x equals 0. And I'm stacking up all these slices, and I'm going to stop stacking them at x equals 2. So my bounds of integration are going to be 0 to 2. And then this would be fairly straightforward to calculate, but the question specifically said do not calculate the integral. Do not evaluate the integral, just set it up. Okay, this one, set up an integral to find the volume of the solid, pictured below left. 2 pictures below right are help us set up the integral needed to find the volume, but we do not need to evaluate the integral, just set it up. Okay, so I'm looking at this, this picture right here. It looks like a cylinder, or half a cylinder, but I'm going to calculate its volume by slicing it vertically. So my slices kind of look like boxes, like a shoe box. It is a little bit curvy, but if you make it really, really small, the curviness becomes less important. Okay, so the volume of each slice, right? This is my shoebox looking thing. This is redrawn here just to make it like really clear looking at it, this shoebox type thing. Its volume is going to be length times width times height. The length of this shoebox is 2x. So this distance is x, 2x. And the width is 10 because this goes back 10. And the height is delta y because this is a height of y and then this is delta y. Okay. So now I'm supposed to use the Pythagorean theorem to solve for x in terms of y. So I've got this triangle pictured in my diagram. The height of my slice is at y, and then the width, half the width is x, and the radius of this thing is 7. That was given in the initial diagram, 7. So if this distance is 7, then so is this distance. It's a radius of a circle. Okay, so I've got x squared plus y squared equals 49, 7 squared. I'm supposed to solve for x in terms of y. So solve for x. So x is going to be the square root of 49 minus y squared. And then we're going to calculate the volume of the slice. So length times width times height. Length times width times height. This is volume of the slice. The length is 2x, but instead of x, I'm going to use this radical 49 minus y squared. And then the width is 10, and the height is delta y. So the volume of my slice is 20 square root of 49 minus y squared delta y. So then to find the volume of the entire solid, I sum up the volumes of all my slices, take a limit as n goes to infinity, and I'm going to translate this to an integral. So this becomes 20 radical 49 minus y squared dy. The delta y becomes a dy. And then my bounds of integration, I'm going to go back up to my picture. And I've got these rectangular slices that I'm starting to create on the bottom, and I'm stacking them up from 0 up to the height of this thing. And the height of this thing is 7. So I'm going to integrate from 0 to 7. Okay, set up an integral to find the volume of the solid whose base is the region inside the circle x squared plus y squared equals 4. This is the same base we had in the demo. In the demo, the cross sections were squares perpendicular to the x-axis. Now they're equilateral triangles. Okay, so I've got a couple of pictures here to help you visualize the solid that we're looking at. And we've got a typical triangular slice drawn in the image right here. So we've got some triangular slices here. Okay, so this is drawn at a random x value, x sub I, and this distance, this is y and y. So my distance is 2y. So the whole triangle, it's equilateral. Every side has length 2y. And the thickness is delta y. I'm sorry, the thickness is delta x because I am drawing this at a random x value. So when I make it a little bit thicker, that is a change in x. So the thickness is delta x here. Okay, so I want to find the volume of this prism, this triangular prism. So the volume of a prism is the area of the base times the height. The height is delta x. So I need to find the area of this equilateral triangle. So let's see, I'm going to drop a perpendicular. So this is y. My hypotenuse is 2y. We'll call this h. So h squared plus y squared has to equal 2y squared, which is 4y squared. solve for h. So h is 4y squared minus y squared. Sorry, h squared is 4y squared minus y squared, which is 3y squared. Right? Those are like terms. You can add them. So h is the square root of 3y squared. But that's the same thing as square root 3 times the square root of y squared. And the square root of y squared is just y. So h is actually square root of 3 times y. So the volume of my slice is the area of the base, which is an equilateral triangle, 1/2. The base of that triangle is 2y. The height of that triangle is root 3y. And then the thickness of that triangle is delta x. Okay, so the problem, I have a problem in that I have y's and x's in this formula for volume. So I'm just going to simplify this a little bit before I try to solve the problem of having y's and x's. My 1/2 and my 2 cancel, and y times y is y squared. So this is root 3 y squared delta x. That's the volume of a slice. Okay, so I can't change the delta x because that's the nature of the way I'm building the solid. I'm building the solid with triangles that are perpendicular to the x-axis. So I'm stacking these triangles up along the x-axis. Each one has thickness delta x. I can't change that thickness of delta x. So instead of using y, I'm going to use the equation of the circle to rewrite y in terms of x. I have an equation that relates y and x, right? I know that x squared plus y squared is 4. That was a given equation of the circle. So I'm going to solve for the y. Y squared is 4 minus x squared. And in fact, that's what's in that's the expression in the volume of my slice, y squared. So the volume of my slice is root 3. Instead of y squared, I'm going to put 4 minus x squared delta x. That's the volume of my slice. Then I'm going to, I guess the sub I, add up all my slices, take a limit as n goes to infinity, translate this limit of a Riemann sum to an integral. So this becomes root 3 times 4 minus x squared. You drop the x, you drop the sub I, delta x becomes a dx. And then let's think about the bounds of integration. Go back up to the picture. So I'm building these equilateral triangles along the x-axis, starting at -2. I'm stacking up these triangles from -2 to 2. So those are my bounds of integration, -2 to 2. And again, this wouldn't be too hard to evaluate that integral, but you're asked not to. Just set up the integral and move on. All right, number 4. Set up an integral to find the volume of this hemisphere of radius 5 shown. So we have a formula for the volume of a hemisphere, but like maybe you don't remember it off the top of your head. We can also calculate the volume of this thing using slicing. So I'm going to slice horizontally because then each slice is a small cylinder. It's a cylinder with just has a very small height. So each slice has a radius r. It's not always 5 because the radius gets smaller as you move up the height of the hemisphere. So the volume of each slice is pi r squared delta h. Right? So the volume of a cylinder is just the area of the cylinder, the area of the base of the cylinder times the height of the cylinder. The height is delta h, and the radius is r. All right, so I have this same problem that I had in the last example. I have 2 different variables in my expression for volume. I have an r and an h. So I'm going to draw a little, add a few lines to this picture. This is H, right? So that was labeled for me. That's H. If I draw this line in, I know it's a 5 because that's the radius of my hemisphere. If this is a 5, then so is this because it's a radius. So that's what I have drawn in this second picture over here. H, R, and 5. So H squared plus R squared equals 25. So R squared is 25 minus H squared. So I'm going to go back over to my formula for the volume of a slice, pi. Instead of R squared, I'm going to put 25 minus H squared, delta H. And these are really H sub i's. Okay, so that's the volume of a single slice. So the volume of all slices is just a sum where every slice has the formula pi times 25 minus hi squared delta h, and I'm going to add up n of them. Then my exact volume is the limit as n goes to infinity of this sum of all my slices. And that is the definition of an integral. That is a limit of a Riemann sum. So that's the integral. Translate, this is pi times 25 minus h squared dh. And my bounds of integration, let's go back up to the picture. H is starting at 0. My very first slice is going to be down here, cylindrical slice. And I'm going to stack these slices up, starting from when h equals 0 until h is 5. The height of this hemisphere is 5. So I'm going to integrate from 0 to 5. Okay, last one. I want to use horizontal slices to set up a definite integral to calculate the area of this isosceles triangle. All right, so this is an isosceles triangle. It has a base of 10 and a height of 5, so we can very quickly calculate its area is 1/2 base times height is 25 square centimeters. But I'm going to overly complicate this with some slicing just to show that you get the same thing. Okay, so each of my slices is going to be a horizontally sliced rectangle, and I'm going to add a bunch of these rectangles up. So I'm stacking a bunch of these rectangles up here, so it'll look like this. All right, so I have drawn, you had one representative rectangle drawn for you. So let's see, this representative rectangle. It has a width delta h, height delta h, and then this is wi, right? The width at h sub I. So the area of this thing is just w times h. It's the area of a rectangle, wi times delta h. But this is a problem because I have w's and h's. I don't want to have w's and h's. I can only have one variable to make integration work. So let's see, I'm going to erase this and see if I can figure out how to relate w and h. And my hint was to use similar triangles. So I have a big triangle and a similar little triangle at a height of h. Okay, so my blue little triangle, this distance is 5 minus h, I'm told. Right, so that's 5 minus hi. And its base is w sub I. And then my big triangle that is similar to the little blue triangle, it has a height of 5, right? The height of the whole thing is 5, and its base is 10. So I can set up a proportion, small to big equals small to big. So The height of the little triangle is 5 minus h sub I. The height of the big triangle is 5. The base of the little triangle is w sub I, and the base of the big triangle is 10. So I have a proportion that relates h's and w's. So I need to solve this thing for w. So I get 50 minus 10hi equals 5wi. Divide both sides by 5. So wi is 10 minus 2h. So I come back over to my formula for the area of a slice. W sub I is 10 minus 2h sub I times delta h. So that's the area of a single slice. I'm going to add a bunch of these slices up, n of them. So the area of all slices. This is the sum from I equals 1 to n. I'm going to add up n slices. Each of those slices has area 10 minus 2hi delta h. And then my area exact is calculated by taking a limit as n goes to infinity. And that is the definition of an integral. That is the limit of a Riemann sum. So this is the integral of 10 minus 2h. Drop the sub I. Delta h becomes dh. And then for the bounds, I'm going to go back up to my picture. I'm integrating with respect to h. So the smallest h can be in this picture. So I have h's labeled over here on the right. H starts here and goes up to the top. So the smallest h can be a 0, and the largest h can be is 5, because that entire distance is 5. So I'm going to integrate from 0 to 5. I'm stacking up these slices from the bottom of the triangle at h equals 0. Stacking, stacking, stacking. I'm stacking these up until I hit the top of the triangle at h equals 5. Integrate from 0 to 5. All right, so let's evaluate this one just to make sure it agrees with our formula that we did earlier. So the antiderivative is 10h minus h squared. Evaluate from 0 to 5. Plug in 5 and you get 50 minus 25 is 25. Plug in 0, you get 0. So the area should be 25. That is the area of this triangle. Right? This should be 1/2 times 10 times 5, which is 25. So my slicing technique works.